So climate change is without question a very controversial subject. I doubt if everybody in this room has the same view on climate change as everybody else. Unlike most areas of mathematics, when I do climate change work, I come into contact with all sorts of different people, including American politicians. So it is important, and it is a meeting point of scientists, mathematicians, and policymakers. Today I'm going to talk about the mathematics behind climate change, but I'd like to just advertise the fact that Gresham College has a professor of environmental science, and you can go and hear lots of wonderful lectures by her on the impacts of climate change on the environment. But today I'm going to talk about the models that are used to help us understand what is going on. So about a month ago, the IPCC produced a big report. They produce a report once every 4 years on the future of the climate over the next few decades. And they base their report on climate models. But climate modeling is really hard, it's really uncertain, and we lack much of the data that we need. And what I want to do in this talk is take you through some of the difficulties, the uncertainty, and the way we make use of data, but to show you how mathematics can help us make certain predictions about the future. So what we see here is what's called an Earth system model. It's a model of everything. Okay, it's quite a big thing. And over on the right here is what I'm going to talk about, which are global climate models, where we try to understand how the climate is going to change by looking at things like the atmosphere and the oceans. But when a policymaker has to make decisions, they need to do more than that. They combine that with an integrated assessment model where they look at the effects of climate on things like the economy, agriculture and energy. And then the hardest thing of all is to understand how all of this impacts on human behaviour. Okay, really hard. In this lecture, I will talk about this bit here, which is in a sense the easy bit of the triangle. And in 2 lectures' time, I'm going to try to do my best to talk about this bit over here when I look at the way that cities and human beings in cities behave and interact with each other. So today we get this. In 2 lectures' time, I'll try and go over here. In my day job, I do a lot of work with the Met Office. And the Met Office has in the same building a thing called the Hadley Centre, which does climate modelling, and the Met Office and the Hadley Centre are essentially 2 halves of the same organisation. And the Met Office and the Hadley Centre together use what we call a hierarchy of models to predict the weather and the climate. There isn't really a difference between weather and climate. Climate is what we expect to get, weather is kind of what we actually get. Okay? But what we mean by that is weather is something I'm going to predict for tomorrow, and we'll test tomorrow by checking whether my forecast is okay. Climate is saying what's going to happen over much longer time scales and over longer spatial scales. So these are various models that are used by the Met Office, and down here, over short time scales and very good resolution, that's small length scales, we have modern weather forecasting models. So this is one I work with a lot, it's called MOGREPS, UKV, UK4. These are the sort of codes that are used by the Met Office every day to forecast your weather. If we go to much longer time scales, like 100 years or more, which is what we need to be able to forecast the climate in such a way that policymakers can take action and look at kind of in detail, which are these things over here, where we're trying to look at whole Earth systems and coupled models, we get these things here, like HADGEM, 3, which is kind of the best one we got at the moment, and that will work over 100 years and over length scales of about 100 kilometres. So this is the sort of stuff that's going on in the kind of scientific world to try to understand the way our climate is changing. And as we get into this lecture, I'll be able to tell you a bit more about some of the worry bits going on inside these, and we can start to make an assessment about whether we believe them or not. Okay. But I thought I'd start the lecture with a little bit of the slightly controversial evidence for why most scientists think that the climate is changing. So we're going to have a look at some what we call official indicators of climate change. This is what the IPCC uses to base its recommendations on. Okay, well, until recently, climate change wasn't called climate change at all. It was called global warming. And one of the key indicators that the climate is changing is that things are getting warmer. So here's a picture I really like. This is a picture of the temperature of the Earth over the last 2,000 or so years. Now, just to explain a bit about this picture, the Met Office was founded about 150 years ago. And what's interesting is that the guy that founded the Met Office was the sea captain of the boat that HMS Beagle that Darwin sailed to the Galapagos in. So that was Admiral Fitzroy. There's a kind of nice link there. So modern weather forecasting and modern data is 150 years old. If you want to go back further, we use what we call proxy data. So we might look at tree rings, for example. The thicker a tree ring is, the warmer the season. We might look at ice and measure the amount of oxygen of certain isotopes in the ice, and that again tells us what the temperature was. Or you might have historical data, such as French wine vineyards. You get a lot of interesting data from them. And well, you do. It's a bad harvest. They sure as hell know. Okay. So by using proxy data, you can go back a long way. We'll look presently at going back over 1 million years, but this is going back 2,000 years. Here we have various different graphs, and the reason you have different graphs is that proxy data can give you slightly different answers. And this is the temperature relative to the mean over that time. So in the Roman times, it was low, and then it warmed up. And the sort of medieval period basically got going because the temperature warmed up. And then it cooled down. This is really interesting. And that was we call the Little Ice Age. And there are pictures of people skating on the Thames by Bruegel and so on. And you can definitely see it was colder then. So it cooled down quite a bit. But then, since about 1800, which is when the Industrial Revolution got going, the temperature has been going up and up and up and up until I think 2016 was the warmest year on record when that graph was taken. So the temperatures are definitely going up. If we look at the kind of measured data, this is the data that the Met Office has actually gathered over the last 150 years or so, we see that the temperature goes up and down. It goes up and down for all sorts of reasons. El Nino is one. That's periodic warming of the Southern Ocean in the Pacific, and that's mostly due to ocean currents. Volcanoes can make things go up and down quite a bit. But overall, we have this increasing trend. The red shows the kind of averaging, clearly showing that the temperature is rising. And you can see the last few years, it's been rising very, very fast. Okay, so the temperature is definitely going up. So that's our first indicator that the climate is changing. Here's a second indicator. This is quite a worrying indicator. So last week I was in Canada, and in fact I gave a dry run of this lecture in Canada, and the Canadians are very concerned about the change in the ice in the Arctic. The reason they're worried is that it's melting. And as it melts, parts of Canada that no one was particularly interested in suddenly become rather interesting, and the Americans and Russians want to claim bits of Canada. Okay, so the Canadians are moving population there to claim it and make sure the Russians and Americans don't grab it. So here's a picture of the ice in the Arctic in the summer, and you have this sort of general ice cover here, but over the last few years, that coverage has been dramatically reducing. Here's the average extent over that time has almost halved. That is a really big reduction. And we can now get ships through here, and that's why the Canadians suddenly get quite interested and nervous. And that is a very measurable thing. We'll go back and we'll have a look at this a bit more later on when we look at some modelling. So the Arctic sea ice is definitely going down. And that has all sorts of effects on the climate. One of the effects is that we get much more fresh water entering into the Atlantic, and then that changes the circulation patterns in the Atlantic. There's NASA's conclusion from its measurements. The Arctic sea ice not only has been reducing in area, but has actually been getting thinner by about 43% in the last 25 years. And this trend is continuing. What's kind of interesting, I've also given talks on climate in New Zealand. And in New Zealand, they're primarily interested in the Antarctic. In the Antarctic, the sea ice is increasing. There is more ice around Antarctica than there used to be. And the reason for that is that the land ice, the ice actually on the Antarctic continental shelf, is melting and flowing out into the sea and forming sea ice. So the ice on the Antarctic is decreasing. And that's actually almost more dangerous than sea ice melting for reasons I'll talk about in a second. So that's our second indicator. Here's our third indicator, more extreme storms. I imagine you've probably noticed we are getting more storms. Okay. This is a very famous one. This occurred in 2014, the St. Valentine's Day storm. And the effect of this was that it cut off the southwest of England from everywhere else. Now, I had a very interesting thing happen to me because of this. I was organising a workshop at my university, the University of Bath, and the title of the workshop was The Effects of Extreme Weather on the Transport Network. I had to cancel the workshop because of the effects of extreme weather on the transport, and I felt that that cancellation told more than anything else. So the Met Office couldn't get to me because of the weather, ironically. So this is the St. Valentine's Day storm. This is the effect of that down in Torquay in Devon. And as I said, the railway network was cut in half and we were isolated for some time. And I couldn't get to London, couldn't get anywhere. And my university is on top of a hill, so we were kind of okay, but there were a lot of floods. Are these an indicator of climate change? Almost certainly yes. Let's have a look at some statistics. This is a count of the number of storms in the North Atlantic. A tropical storm has to have a certain intensity to count, and then you can just see how many you get. And here's the kind of figures that you're getting, which were kind of jogging around underneath this level. And then in recent years, the frequency has absolutely gone through the roof. So we are certainly getting more extreme weather events. If we look at temperature, again, the number of extreme heat events is increasing. And actually this is worrying. Storms, flooding, devastate property, kill a few people. Heat events kill people in the tens of thousands. So in the 2003, there was a heat wave in Europe and thousands of people died in that. So it's something we worry about a lot. And as you can see, the frequency of extreme events is certainly increasing. The reason behind this is to do with statistics. When we talk about global warming, the IPCC and the Paris Agreement have said that we need to keep average temperatures below 1.5 increase degrees. So they want to reduce the increase in average temperatures to be below 1.5 degrees centigrade over the next decade or so. You might think 1.5 degrees, that doesn't sound like very much, but it actually matters. This is a picture of what kind of happens when you change the average of something by a small amount. This here is a bell curve showing the kind of probability of getting, let's say, a hot day. And the probability is what we call a normal distribution. This is the kind of average here with the highest probability. And the hot events, that would be a kind of probability up there. If you change the mean, so you change the average temperature by 1.5 degrees centigrade, this curve moves over to the right. And this bit, which is what we call the tail, moves up a great deal. So a small move to the right lifts the tail up a great deal. And what that means is that the probability of an extreme event goes up far more than just the small change in the mean. It's in fact proportional to the exponential of the mean. So a small change in the mean value means a large change in extreme events, and therefore that is why we're getting more and more storms. It's extremely consistent with that sort of analysis. Sea level rise. This is again something we can measure. You can measure it by measuring tide tables or by satellite directly looking down on the sea. And this is the sea level rise over the last 20 or so years. And it's gone up. Actually, it's gone up a lot. It's gone up by 80 millimetres. So it's quite a significant amount. And there are two reasons why the sea is rising. One is as things get warmer, so water expands, and therefore the sea level rises. And secondly, as ice melts from land, from Antarctica, and goes into the oceans, it raises the amount of water in the oceans, and therefore the water goes up. Sea level does not change due to Arctic ice because that's floating on the water already. But there we go. It's going up at a rate of about 3.5 millimetres a year. Now, in an extreme case, if Greenland was to, say, melt, and all the ice in Greenland was to dump into the sea, and all of Antarctica was to dump into the sea, this is what the Earth would look like. The blue here shows the areas which will be underwater. So I'm afraid to say Gresham College is not looking good. Okay. You might want to move to the University of Bath. Okay. And we'll probably all have to relocate to Africa or something like that in order to keep away. So that is an extreme case, and that's what would happen if Antarctica and Greenland went. But as I say, there's no doubt at all that sea level rise is happening. And the final indicator of climate change is atmospheric carbon dioxide. Now, there's a certain amount of controversy about the link between carbon dioxide and climate change. It's something I'll come on to towards the end of this lecture when we start looking at climate models. But there's no doubt at all that atmospheric carbon dioxide is increasing. There's an observatory in Hawaii on top of a mountain called the Mauna Loa Observatory, which measures the amount of carbon dioxide in the atmosphere measured in terms of parts per million. And in 1960, it was 315 parts per million. Now it is 407 parts per million. So it's gone up nearly 100 parts per million, or a third, since 1960. So that's a huge increase. This is a graph. The oscillations here are just the oscillations due to the seasons. And you can see it went through 400 quite recently and is just charging on upwards. And it's going on upwards faster than a linear rate. So it really is increasing. That's the last 50 years or so. if we look at the amount of carbon dioxide in the last 1,000 years, which again you can measure by proxies, you can measure the amount of carbon dioxide, for example, in ice. So that gives you a very clear idea of how much carbon dioxide was in the atmosphere. This is the last 1,000 years. You can see the carbon dioxide level was wobbling around about 200 parts per million. Then we get to the year 1800, which is when the fossil fuels were starting to be burnt in large amounts due to the Industrial Revolution. And you get very, very rapid rise in carbon dioxide over that time. This is called the hockey stick in climate circles. What's really important about this graph is not so much that it's risen. Carbon dioxide goes up and down over millennia, we know that. The fact is that it's risen so fast. And we're not sure at all whether the Earth's systems can cope with that rapid rise. And again, we'll come back to that when we look at models later on. There's definitely a correlation between carbon dioxide concentration and temperature. Again, this is Met Office data, so we can be pretty sure it's correct. Over the last 150 years, here's temperature, here's carbon dioxide in synchrony with each other. Of course, there's the question, does temperature lead to carbon dioxide rise, or does carbon dioxide rise lead to temperature rise? I'll talk about that later on. So there we are. There's, I feel, a lot of evidence for something happening, but you only have to listen to certain American politicians to realise that not everyone agrees. And it's fair to say that the evidence for climate change, whilst strong, does have issues associated with it. And certainly it's true that not everyone agrees with climate change. So after an article was published that temperatures have gone up very rapidly, What's Up With That, which is a climate-denying website, said this is nonsense, there have been no statistics for at least a decade. And there is the Daily Express saying 100 reasons why global warming is natural. Not sure what Simon Cowell has to do with it. And just to show that things are controversial, Daily Express again, big climate change fraud. So a few years ago, a group of enterprising individuals hacked into the University of Norwich Climate Centre and downloaded a whole load of emails from the climate scientists and found that they used words like trick. In other words, any scientist like me says, well, we use certain tricks to do things, meaning shortcuts. They thought, trick, aha, and it must be all wrong, and made a big thing about it. So it's certainly not something everyone agrees with, although it's fair to say most scientists do believe that climate change is happening. And climate science is hard for a number of reasons. One is elegantly stated by Niels Bohr. I referred to this last lecture when I talked about predictability. It is difficult to predict anything, especially about the future. This quote is also attributed to Yogi Berra, the baseball captain. Okay. And here are 4 reasons why climate change is hard. Firstly, there is data out there. Some of the data is definitely dodgy because you're trying to learn about things from, let's say, looking back into the past where we're not quite sure what happened, or in Antarctica where it's difficult to get measurements. And all data has statistical variation, and somehow you're trying to extract trends from data which is varying. And we'll have a look at that in a minute. A second reason, hopefully many of you came to my lecture last month about chaos. There is a natural unpredictability in all complicated systems. Third reason is that climate science is genuinely complex. There is an awful lot going on. The models that we are currently using probably have billions of degrees of freedom and have millions and millions of lines of computer code. If you've ever written computer code, you'll know how hard it is to write anything without errors. And it's almost certainly true that every climate model has got errors in it somewhere. We just hope that they're not important. And the final one, and this is something which climate skeptics often worry about, is how much of the climate change that I've talked about is due to human activity and how much of it is going to happen anyway, due to the Earth's natural variability. So I'm going to have a look at all of these, and then we'll go on to the business of how we construct a climate model. So let's have a look at the data issues, and we'll go back to this question of the Arctic sea ice to see how we might make predictions from that. And we're going to have a look at some data that NASA produces. So they have this National Snow and Ice Data Center, which has satellites which orbit the Earth and look downwards on the ice and do things like measure the area of the ice. So in the first 4 years of the operation of the satellite, it measured the area in millions of square kilometres, and that was the graph that they got. And it's not unreasonable, looking at that, to say the amount of ice is slowly increasing. Okay, it's gone from 8.1 million square kilometres to 8.5. Okay, if we do the same thing over 10 years, there it is going up, and then it dramatically fell, and then went up again, and so on. And the best we could reasonably say from that 10 years is that the amount of ice is about constant. Okay, let's go a bit further. Over the next 20 or so years, we go up, we go down, we go up, we go all the way down, we go and all the way up. Again, there's some indication that things might be going down, but again, no one could absolutely for certain say on that amount of data. And there we are. If we'd use that, then we might conclude that nothing is really happening up in the Arctic. It's just slowly going up and down. But if you look at the last 30 years, a very different picture emerges. We see this variation, but now, as we look at more and more data, a very clear trend is emerging. And if we go right up to the date, you can see this trend is absolutely clear, that the amount of ice is going down, and it follows this monotonic downward trend. So you really have to kind of wait a bit with climate models to check that what's happening is happening, and it's not just statistical variation. The next slide's a bit worrying. If we continue that trend, then by the end of this century, all the ice has gone. In fact, I have colleagues in the Hadley Centre who have different models that predict all the ice will be gone in 30 years. So this is definitely something to worry about. But it shows how you need to kind of wait a while and be very careful about the way you make predictions based on the sort of data that we have. Last month, I talked about chaos. If you recall, I swung a pendulum. If you weren't here last month, go on to the Gresham website, have a look at my lecture. You'll find I swing a pendulum around. Climate models are what we call nonlinear. They have lots of feedback mechanisms in them. So increasing temperature means that rainfall patterns change, which means the temperature change. You've got this sort of feedback mechanism. And when you have nonlinear systems with lots of interacting things, they're not always particularly predictable. It is a fact that we cannot predict the weather more than a week in advance with any sort of accuracy. Don't let anyone tell you can, because we can't. I can give you the weather tomorrow pretty accurately, in 5 days reasonably accurately, but after 10 days it's random numbers. And a normal objection that's made against climate modelling is if you can't predict the weather due to the nonlinear interactions and the resulting chaos, how on earth can you predict climate? And that's true enough, but what that means is that I couldn't predict in 10 years' time what's going to happen on the 13th of November in 10 years' time. It could be almost anything. It'll probably be cold and wet, knowing it's November. But what climate modelling can do is say there will be an overall trend in what's happening. So I can reasonably certainly predict that in 10 years' time, the average temperature in November will be higher than it is today, and the rainfall will probably be higher as well due to these extreme events. So climate modelling is all about average trends and the way things are generally happening. As I said before, climate is what you expect, but weather is what you get. Okay. I also expect in 10 years' time, we're going to be able to predict the weather a bit more accurately, and next year when I talk about the future of computing, I'll talk a bit more about why that is so. Here is this other issue that is often talked about with related to climate change. How can we tell what is natural? How can we tell what is man-made? And one way we can get some idea is to go way back into the past and have a look at how the climate has changed over millions of years. Again, you might say, how can you do that? Well, the way we do that typically is we drill down into the ice in Greenland or in Antarctica. You extract ice cores. You can see the years in the ice cores by the layers and also by electrical measurements. You can measure the amount of oxygen. You can measure the amount of carbon dioxide, and that tells you a lot about the temperature and also the general amount of ice that there was on the Earth at that time. So this is one of my favourite and rather famous picture. This is showing what the climate's been doing for the last 500,000 years. So I'll just take you through this. There we have 450,000 years ago up to the current date. Here we have temperature measurements as determined by one ice core called the Epica ice core. Here's the temperature from another ice core called the Vostok ice core, so that allows us independent measurements. Here is an estimate of the ice volume on the Earth by looking at the ice cores, where we've got low here and high here. And what's remarkable about this picture is we see a strong degree of regularity, what we call periodicity, in the climate. So the climate over the last 500,000 years has been going like a clock. And essentially, every 100,000 years, we have what we call a glacial cycle. And in the glacial cycle, we have a sudden warming, so the Earth goes up by about 10 degrees. Sudden means over a few thousand years. And then we have a slow cooling over a period of about 100,000 years. So we get this warming, cooling, warming, cooling, warming, cooling cycle, regular as clockwork, every 100,000 years. There are oscillations as well, and these are largely due to ocean current changes. Here we are at the present day. We came out of an ice age about 10,000 years ago. That's called the Younger Dryas Ice Age. We're now in a thing called the Holocene, where we're about here, and if nature was left to itself, we'd be starting a slow decline in temperature. That's the last 500,000 years. Here's an interesting graph. For some reason, some climate papers do time going from left to right. Others do time going from right to left. This is one of those. So here we have time over here. That's 2,500,000 years ago going to the left. There's the current day here. Again, looking at ice core measurements, and this is interesting. We see a rapid oscillation. These are small but rapid oscillations in the climate over about 40,000 years. And then around about 500,000 years ago, something happened. We're not quite sure what. And then we move into this ice age of 100,000 year cycles over here. This thing here is called the Mid-Pleistocene Transition. I want to say this is something which we're very interested in at Bath, and many people are interested in. And we have a look at models for this and see whether we can explain or predict this. And one of my PhD students, Susan Morapisi, who's actually here in the audience, has worked on this and this is some of her own calculations using climate models. And the evidence here is that there is something like that happening, a mid-Pleistocene transition. And the reason we think is that the climate can basically exist in a number of different states. Each state is stable, and you can get transitions from one state to another, and that's occurring around about here. So we may have some idea what's going on, but we're not sure completely. But the key thing from this graph is that nature left to itself would be starting to cool down around about now, because we're entering into another full glacial cycle. Okay, and one of the reasons for this is due to the variation in the amount of radiation that we get on the Earth's surface. So the sun itself varies slowly, but as the Earth goes round the sun, it wobbles on its orbit, and the orbit changes as well. You have here various combining effects, which means that the amount of radiation that comes to the Earth from the sun actually varies over periods of tens or hundreds of thousands of years, and this contributes to the way that glacial cycles occur. The link isn't at all clear, and that's what Susan and I and others have been working a lot on, but it's a very important part of that. So the key sort of thing I want you to kind of think about here is that the effects of solar variation and various other things, combined with looking at past data, would indicate that the Earth should now be cooling rather than warming up. So the fact it's warming up is very likely due to human activity. And one of the ways that we test climate models is that you run them on past data. So the Hadley Centre took the Earth's climate in the year 1900 and ran forward their model with that as initial data, and they ran it forward in two ways. One, without putting in carbon dioxide from measured values, just keeping the constant values at 1900. Another was putting in the actual measured values. If you put in the actual measured values, the climate that you predict is what you see. If you take out the measured values and keep them constant, then the Earth would actually be significantly cooler than it is now. So from that alone, we can see that the warming is almost certainly due to human activity. Okay, so I've started to mention climate models. Now I want to get on to kind of this part of the talk where I can show you how these models are constructed. All climate models are based on the laws of physics. Okay, that is how they operate. A climate model is based on the same laws of physics as a weather model, and one of the tests we have for climate models is that in a weather model, we test that model every day by comparing it against the actual weather. So if there was a major error, we would spot it pretty fast. So a climate model is based on the same physics, broadly speaking, as a weather model. What's that physics? Well, it's Isaac Newton describing the laws of motion, particularly of the air and of the oceans, combined with Kelvin, the great Irish scientist who in the 19th century worked out the laws of thermodynamics, the laws of heat. So these two combine, we turn them into partial differential equations. I'll show you these equations in a minute. And then these are solved on supercomputers to predict the climate. Just a small fact, the current supercomputers that are used by the Met Office and other climate centres to do all their calculations do trillions of calculations a second and take megawatts of energy to do this. Supercomputers are a not insignificant component in modern global warming. Okay. So we try and watch that. In a climate model, what you do is you try to assess all the different things that are going on, like things like air pressure, air velocity, and so on. You build in solar radiation and so on and so on. You take all these quantities and you write down differential equations to describe them. And the next slide is the key mathematical slide of the talk. That is the equations. To be accurate, those are the equations for weather. So these are the equations that the Met Office solves every day to predict your weather. These are the equations that I, when I'm doing my research, try to advise the Met Office on how to solve accurately. This is momentum, density, temperature, moisture, and pressure. These are the equations we're pretty certain we understand because they are the weather equations. And then what you do with climate is you add into these equations all the other complexities of what's going on. I'll whiz forward so I can get onto that. And this is the sort of complexity you might add. So in the 70s, they were putting in carbon dioxide and rain and so on. And then in the 80s, starting to look at the effects of vegetation and ice. And later on, starting to look at really quite deeply into the chemistry of the atmosphere, the effects of plant and soil, biology in the ocean. Plankton in the ocean is really, really important contributor to the way carbon dioxide moves around the planet. And these are all tested mostly by comparing them with past data. This is what we call hindcasting, where we take one calculation, we look at the climate in the past and see whether we can reproduce it. Okay. And that's how they're tested. I have certain worries about this. It's extremely easy to predict something in the past. Okay? Really easy. I know exactly what the weather was on the 13th of November 2013, for example. So I worry a bit about this. I also worry about the fact that our codes are so complicated. And what is typically done is that we look at a whole range of models, from simple models to complex. I call these good, bad, and ugly. So a good model is something where we can test it, we can make predictions, and we can compare them against the data. A bad model is something where you basically can't do that, and I would regard most of our modern climate models as ugly. They're somewhere between. They're very complex, and you can test some bits, and you can't test others. Okay. But this is a trade slide from the Met Office showing where we are at the moment with all the complexity. Every single one of these would be thousands of lines of code combining together to give these complicated climate models. And each of these we try and test individually to try to build up a reasonably reliable thing. But modern climate modelling, not only does it try to predict things, but it also tries to estimate the uncertainty in the predictions that you make, and also what we'd call the sensitivity in what you make. So if you do change the data a bit or change parameters, we understand how the answer would change as well. I can't take you through a full climate model. That would take forever. But what I want to do is have a look at some of the simpler models to give you some idea about how we can formulate them and test them. And this is a sort of hierarchy that we have of current models. So there's the Earth system model that I introduced at the beginning of this talk, where you've got a very, very complicated thing with lots of things going on. These are the global climate models, which is what the Met Office works with. These are reduced climate models, which we use for testing, down to quite simple models. And the EBM, the energy balance model, is one I want to tell you about now, which is simple, we can test the physics, and yet is still quite predictive and allows us to make certain predictions about the effect on the climate of varying things. So let's have a look at an energy balance model. An energy balance model makes the assumption that the Earth is a single body with a single temperature. In other words, you average the temperature of the Earth out over all the different countries and over all time. So you have a single temperature measurement which will vary slowly, but we average out the daily effects and also across the continents. We then look at the energy coming into that system, which can only come from one place, which is the sun, and the energy coming out of that system, which is due to the Earth releasing energy back into space. This lovely picture, due to these people over here, shows the key thing is this number here, 342, which is the amount of energy that comes into us from the sun. That energy typically comes in short wavelengths. It then heats up the Earth, and that energy is then radiated back out into space. Some of it's absorbed into clouds, some of it gets all the way out into space. Some of it simply gets reflected from the clouds, so 107 watts per square metre gets reflected from the clouds, and the rest comes out as infrared back into space. So these are the energy balances in the Earth, and this is good solid physics. You go and measure all this. So what you have here is the heat from the sun, I shall call that S, warms up the Earth, and the Earth radiates that out into space. Okay. Very simple system. I'm not looking at any variation over the Earth at all. We can write down formula for this. So the heat absorbed by the Earth is the amount coming in from the sun minus the amount that is reflected. So the amount reflected by the Earth is called the albedo, A, and the amount we absorb is 1 minus the albedo times S. The current albedo is about 0.3. So we absorb 70% of the energy that comes in from the sun. The Earth then heats up and acts as what we call a black body, radiates it out into space, and the amount radiated is the fourth power of the absolute temperature times a number called the Stefan-Boltzmann constant times a number E, and the E is the proportion of the radiated energy from the Earth actually getting into space, because a large proportion of the energy radiated from the Earth is reflected by the clouds. So the amount getting into space is about 30% of the amount radiated by the Earth. If we were on the moon, it will be more like 100%, because the moon doesn't have an atmosphere. An energy balance model simply says, okay, let's balance that with that, and we get this formula here. Okay. And this is a nice formula. It's a formula we can solve on a calculator. If I know what S is, A is, E is, and sigma is, I can find T directly from that formula. Let's have a look. If we take the current values, the albedo, as I say, is about 30%. The emissivity, sorry, I was misquoting, is about 0.6. So 60% gets into space, sorry. There's the Stefan-Boltzmann constant. This number, 342 watts per square metre, is something we can measure. Anyone with solar panels might be aware of this number. If you substitute these in, we get this formula for the temperature. By the way, this is Boltzmann, who came up with this black body radiation law. And we find that the temperature, the mean temperature of the Earth, according to this formula, is 288 Kelvin, and that is correct. Okay, you can go and measure that. And that comes very simple energy balance law. It must be right because it's just energy in equals energy out. So this calculation was done well over 100 years ago by this guy. This is called Arrhenius. If anyone works in chemical engineering or chemical reactions, you'll be familiar with Arrhenius because he did the mathematical theory of chemistry. And he came up with this formula. And this formula is nice and simple. It is also predictive. What this formula predicts is that if the solar radiation increases, so the temperature increases. That's not unreasonable. If the albedo decreases, so less energy is radiated into space, then the temperature increases. If the emissivity decreases, then the temperature increases. And this is the worrying one. Decrease in emissivity is due to the reduction in the amount of energy that the Earth produces being radiated into space. If you put carbon dioxide into the atmosphere, or methane, there's methane coming out of cows, okay? By the way, a significant contribution to global warming is due to animals. There's carbon dioxide. If we increase the amount of carbon dioxide, it decreases the amount of energy going into space because these gases reflect energy back to Earth. And if this decreases, temperature increases. This is a really important equation for me as a scientist because it shows a direct causal link between greenhouse gases and temperature. It's hard to argue against that formula. Just to show you a little bit more, in numbers, the emissivity, the amount of heat radiated back to the Earth, depends upon methane, carbon dioxide, water vapour, and a few other things. The contribution due to carbon dioxide is something you can go and measure. It's a scientific thing that you can go and do. As the carbon dioxide increases, the emissivity definitely decreases. Here's the carbon dioxide graph we looked at earlier, wobbling around about 250 or so before the Industrial Revolution, and then whoomp, straight up to 400 over no time at all. And that is going up. That means that's going down, and that means that that's going up. Okay, and that model clearly predicts it. The problem with this model is that I haven't put in the kind of time variation, but this is so fast in any reasonable climate model that it's essentially instantaneous, and therefore the Earth isn't able to recover. Okay, and that is a direct consequence of this simple model. And we can use this simple model to check that our more complicated models are doing the right thing on average. So what do these complicated models do? Well, we use them to predict into the future. And there are many climate centres around, all of whom are running different models. It's good to run different models. It's good to run different models. It's like the famous story about the Irish railway station that had two clocks. And someone said, why do you have two clocks? Oh, and the two clocks show different times. And someone said, why do your two clocks show different times? And the station master said, well, if they showed the same time, we wouldn't need two clocks. Okay. There's a lot of wisdom in that. And the wisdom here is that by running different models, we can compare one against the other. This blue model here is the American model. NCAR is the National Centre for Atmospheric Research, predicting a 2-degree increase by the end of the century. The brown model is the Japanese model, predicting a 4.5 degree. These are all consistent with varying levels of carbon dioxide they predict going in. And I'm very proud to say that the supercomputer that the Hadley Centre has, this complicated thing and all the energy it's producing, what it's done is it's taken the American model and added it to the Japanese model and divided by 2. And there's the British one up the middle, okay, predicting about 3 degrees. All of which are comfortably more than the 1.5 degrees that the IPCC says safe for us. Just again, show you the way people think. This is the, again, the Hadley model, that's another one of theirs. And what they try to do is build in uncertainty. So all models have uncertainty. You have uncertainty due to the physics that you're modelling, due to the data that you're using, due to the way you solve things, due to the effects of chaos and all that. And these are a kind of temperature prediction with uncertainty. With uncertainty. So the one up the middle is the one I'm most confident on, which gives you this 2.5 degree rise or whatever. And these are the error bars in that. And modern climate prediction is valueless unless this is built in. Okay. Now, I'll just take you a little bit beyond the model I've described and show you what could happen in a somewhat worst case scenario. There's a thing called the Ice Albedo Feedback. And the way this works is that the temperature rises. That causes the ice to melt. As the ice melts, the Earth becomes less reflective because the ice reflects temperature, reflects radiation, and therefore the Earth gets hotter, and therefore the ice melts, and so on. And you go around this loop, and you worry that you'll then spiral out of control and go into a state where everything's too hot or too cold. Okay. What this does is it increases the sensitivity. So the calculation I did earlier, where I changed emissivity, means that with this sort of feedback mechanism, a small change in carbon dioxide can actually have a more significant effect on the atmosphere. And one way we can sort of see this mathematically is here is a model for the albedo, that's the reflectivity, as a function of temperature. So for low temperatures, you reflect almost everything, and for high temperatures, you reflect much less. If you combine that with the emissivity, the earlier calculation, you get this rather interesting picture which shows how the temperature here is a function of emissivity here. Current emissivity is about 0.6. The star indicates where we are. If we change emissivity a little bit by adding carbon dioxide, we'll go up and down here, which means things will change a bit. But what's kind of dramatic is that if the atmosphere changed quite a bit and we took essentially all the carbon dioxide out, we might go down here and suddenly, whoomph, we'd end up on a very cold Earth where the whole thing's covered with ice, and we would have to dramatically pump carbon dioxide into the atmosphere before we go up to hot Earth again. So this is kind of an interesting cycle. There is indications that something like this happened in the past about 600 million years ago, when the Earth was in what we call a snowball Earth state covered in ice. And that's called a tipping point, and there are various other possibilities of tipping points, of big changes, which we worry about. One of them over here is that if we heat up Siberia, it'll melt the permafrost, which will release methane. Methane's a greenhouse gas, so that will increase the temperature, and so you go around there. And so that's a bit of a worry here. So I shall just finish on a slightly more cheerful note. Are we all doomed on the 50th anniversary of Dad's Army? Well, not necessarily. Of course, what all this is doing is helping us understand that something needs to be done, and various things that are being done. One is that there's a lot of work going on about not only reducing carbon dioxide, which is really good, but also capturing what we produce and storing it. Energy harvesting is something I'm very interested in, which is just extracting energy. When we produce energy, for example, those lights produce a lot of energy which we're not using. Can we extract the stuff we're not using and use that for something else? And of course, increased use of renewable energy, which is something I talked about a couple of lecture sessions ago. If anyone wants a really, really good read on this subject, David Mackay, who was the Chief Scientific Advisor to the government on environmental and climate issues, produced a wonderful book called Sustainable Energy Without the Hot Air. And that's free. You can download it from the internet, and is by far the best account of all of this I've ever read. Very sadly, David Mackay died a few years ago due to cancer, but this book is a marvellous testimony to his work. So just to conclude, there's my formula. That's my view on climate change. What as a mathematician can I do? Well, these sort of formulas help us understand the way we do need to change the way we put stuff into the atmosphere and the way we use energy. Mathematical models help us be more aware of what is happening and what we can do. But most importantly, and this is something I really, really couldn't say too strongly, whenever you hear politicians or anyone else talk about climate change, always think and use scientific judgment to try to work out what they're really trying to say and what's true and what isn't. And with that, thank you very much.